Howdy, how's it going? In 1.3, the Ready, Set, Go. I'm glad you're here. We are tracking the tortoise previously in the lab. We'll look at 1, 3, and 5, and we'll do a good portion of the set. Hope you're doing well today. The Ready, you should have seen problems like this. Luckily, you're just solving for X. Some of these bases are already the same, so that's a nice thing. Good thing to check on is, are you working with the same set of bases? Meaning, are the bases both 5 or are they slightly different? Are they a power of 5? Chances are they're going to be a power of some number that's already there. So luckily, since these have the same base, we can just set the exponents equal to each other. You're solving x plus 1 equals 2x minus 3. I'll give you a moment to solve that and see what the outcome's going to be. So hopefully when you balance this out, you get that x equals 4. Hopefully that one was pretty simple. And 3, let's check on this real quick. Are the bases the same? No, not quite, but they could be. Hopefully you know that if you add 2 squared, that equals 4. So you could pop back in here and say, all right, instead of 4, I could write it as 2 squared to the 3x power. And isn't this slowly starting to look as if they have the same base? How do you think you could bring these two exponents together, the 2 and the 3x? Hopefully you're saying multiply them out. So if you have 2 times 3x, that's 6x. Lo and behold, you have the same base. So just set them equal to each other. Solve 6x equals 2x minus 8. Get rid of the 2x. This gets you 4x equals negative 8. So x equals negative 2. If you're not convinced that these work, try them out, but I'm pretty sure that they work. Take a moment, try 5. See, can you rewrite these both so that they have the same base? Give that one a shot real quick, and I'll have the answers here in a moment. So hopefully you got that x equals 0. You could plug back in, you could check it. You said x equal to 1. Your work could look something like this. And then 2 times 0 plus 3. This just becomes 8 to the first power, and this now becomes 2 to the third. So this is really saying that 8 equals 8. That's a true statement. We know we did this right. Capiche? Makes sense? I'll see you in the set. Maybe pause the video, take a moment to read through the story that's here. It's not a bad idea. Maybe pause the video now, see what's up with this story before we talk about it. In the fairy tale, Jack and the Beanstalk, Jack plants a bean before he goes to bed. Jack discovers the beanstalk's grown so large, it's moving up and up and up. I guess this is the story we never heard, that after so many hours of this being planted, the height grew so large. And notice that we also have these half increments here. So 1.5 hours could be, 90 minutes. So this is kind of interesting that it's taking on the halves. And it's also being modeled off of this b of t equals 3 to the t power. B is representing the height of this plant. T is in hours, how many hours this thing is growing for. And we have this table that we'll keep on referencing as we work through this set. So it may help to look back at that. Demonstrate how Jack used this model to calculate the height of the beanstalk after 6 hours had passed. So this is referencing time. And this function is saying, hey, whatever time is, put it in place of t. So 3 to the 6th power. What is that? I'll reference the table because I already put in the work for it. 729. What exactly? Feet. There we go. During the same night, a neighbor was playing with a drone. I guess this is a mix of current day and previous eras. And it was programmed to hover at 243 feet. So now it's as if we have our height, but our time, we don't know. We do have that table. So maybe 243 just happens to be there. Lo and behold, that happens after 5 hours. Pretty simple. So our timer in this case is 5 hours. Did you use the table in the same way to answer 8 as you did 7? Kind of. I mean, with 7, we found where t was 6, and with this, we found where the height, or b of t, was equal to 243. So yeah, I guess you could say that we did use the table for both. This was, your input, and then you were finding your output. So I'll put output question mark. Whereas with this, you knew your output, but you were looking for your input. So input question mark. I guess that's a way you can think about it. Finding table, wondering how tall it would be after the magical 10 hours. Write the expression. Jack would have typed into his calculator. I mean, we already have that function, which was given to us. We know it's 3 to the t power. So I guess in your calculator, I would hope that you do something like 3 to the 10th power and get whatever that's going to be. And no need to approximate it, actually. This should give you some number, which I'll leave it up to you to find. Commercial jets fly between those two increments of height. I'll leave it up to you to try and find that out. There is an increment there, so feel free to reference it. They're doing some find the mathematical interpretation where t is 7, and this is kicking out what's the inverse when your height is this. So f of 7, I mean, we have the table, so just reference what it's like at 7, 2,187. Pretty simple. So that's that. And now this is having us go backwards for 11,364. Hopefully that's in the table. Might not be. Okay, it's not. So what could we do? I mean, you could figure out the rest of this and how this works. Maybe take a guess. Maybe think out, what is this time going to be if you know what your height is going to be. The height in this case, recall, is how much? 11,364. Maybe do that for a second. So try and find out what your input's going to be if your output's 11,364. I'll give you a moment. All right, so you might have had to do a little bit of problem solving for this because the output is going to be occurring at 8.5 hours. And yeah, it wasn't in the table, but that's okay. Because if you kept the idea going, I think you get left off with how much it is at what, 7.5 hours. So if you keep that idea going, you can just throw in some values for your exponent, and lo and behold, it's going to get you 8.5 hours. So that shouldn't have been too bad. 13 is going to use the table again. You're going to work backwards from that. You're then asked down here for 15, is this an invertible function? I'd say yes. Why is that? You could say that each input has a unique output. And you can say each here. So what does that mean? That means that if you were going to test f of 3, which I think is 27, you're never going to have some other increment where it's going to claim that f of 3 is going to be just 9. That's not happening. That would be very conflicting. So every input has a unique output. There's nothing that doubles over. There's actually no repeats in your output. So that's what that means. Graph the inverse on the same set of axes. You need to recall a few things. Recall that inverses reflect over what line? What does it reflect over? Hopefully you're saying y equals x. So it might be helpful to sketch out what that looks like. Sketch it out. In my case, I do this dashed. So this means that all the points over here on this side of y equals x should reflect over to here. And so that means that if you have this point here of 1, -1, the inverse of it is going to have a point of, switched around, -1, comma 1. And you can do your best to kind of make this curved like that. There aren't really any other points, but we know that it should meet back up here. So just do your best to draw a straight line from there to there. And boom, that's it. In blue, this is what's happening. Pretty simple for that. 17, I'll leave for you. 18, I'll leave for you. We'll look at the go. I mean, we've seen these problems a bunch. Maybe this one you need to see a little bit. So this is calculating the indicated function values. So this is f of g of x. So f of g of x. So g of x is 2x plus 5. So this is saying that if you have this modeled out as negative 2x, because f of x equals negative 2x, whatever your input is here, you're now putting that in place of your input from before. So now in parentheses, this should be 2x plus 5. Distribute that out, negative 4x minus 10, and there you go. Not too bad. Let's see if we can find one that has a little bit more going on with it. And of course, why would they write the equations again down here? This one's not too bad. F of b squared, whatever your input is, just put b squared. And luckily you don't have to simplify too much here. So just negative 2b squared is legit. Type to b squared. I mean, the other problems aren't as bad. I mean, you're doing a composite for h of f of x. And you know what? You get the idea. Think about what we did here. Rewrite the equation that's being put in, and then think about what that output or what other equation on the outskirts should look like. I hope that this video was helpful. If you have any questions, reach out. Let me know. Thanks for watching.